transistor is basically the fundamental building block of all these circuits, right? And as a designer, you need to understand what the transistor does, at least at some level of abstraction, right? So the transistor can be studied as a separate course in a device, semiconductor devices course. We are not going to go into that level of detail. I need a certain abstraction that will help me make my decisions in digital circuit design very well. With respect to that, I will teach what is necessary about the transistor, right? How do you get the expression for the current? What affects the current? What are the model parameters that a designer should know about? These kind of questions we will answer in this module. Okay. What are the learning objectives? Okay. Again, once you are done with this module, you should be able to explain short channel effects. It's called SCE, right? So when I bring the channel, when I bring the diffusions very close, right, the channel becomes very small. That introduces some non-idealities. So that is something you should be able to explain, like drain-induced barrier lowering, gate-induced drain leakage, subthreshold leakage, channel length modulation, and so on, right? Then you should be able to derive the equation for the on current of a CMOS transistor with first order short channel effects. Okay, we'll do all of this. Then the most important thing is you should be able to estimate various capacitance and resistance components of a transistor, because ultimately going forward I want to measure delay, and not surprisingly delay of a transistor is just given by R into C. I need to be able to estimate these components and figure out how the transistor behaves with respect to resistance and capacitance. Okay. So the outline, okay, this I am going to just briefly tell you about silicon and doping and the PN junction only with respect to what we need for the CMOS transistor. I am not going to go into deriving the current equation for a PN junction and all that. That's for a different course. Very quickly I will jump into the CMOS transistor and define what threshold voltage is, what the on current is. We will derive what the on current is, channel length modulation, velocity saturation, subthreshold leakage, a host of other short channel effects. So what you see here, right, basically from here, channel length modulation on till reverse short channel effect, those are all the effect of bringing the diffusions very close by. So I'll do all of that, and some leakage mechanisms also, right, that a digital designer should be worried about. And then we'll do the capacitance and resistance estimation. Okay. So with that, let's just quickly jump into the transistor. And of course the semiconductor that is used is silicon. Why is silicon? Because it has good mobility, but it also has a very fantastic thing called a silicon dioxide, which can serve as the oxide insulator, and forming the silicon dioxide is very easy. So the interface is nothing, you just oxidize the silicon, you get a good silicon dioxide there. So that makes the transistor manufacturing relatively much easier compared to if you try to do it with other semiconductors, right? So what is silicon? Basically it has 4 valence electrons, right, which means that in a lattice it's going to sit like this, right, and you have covalent bonds which are connected like this. Okay. And as I increase the temperature from 0 Kelvin onwards, some electrons can break free from this bond and be made available for conduction. This can result in a free electron. Okay. What is now quickly the order of magnitude again? The silicon density is what? Yeah, 10 power 22, right? Per centimeter cube. Okay, in 1 cm cube you have 10 power 22 atoms. Now at room temperature right, which is what, about 27 Kelvin, 27 degrees centigrade, 300 Kelvin. The number of free electrons that are available is basically called Ni. Why? Because it's intrinsic silicon, it has nothing else. Number of free electrons is equal to number of holes. Absence of an electron can be treated as a hole for this course. Number of electrons obviously is equal to number of holes, because I have to maintain charge balance, right? And that is what? Order of magnitude. Again, I don't want 10 power 10 per centimeter cubed. Okay, clearly this number is not high enough for me to achieve the conduction that I need, right? So therefore what you do is you go ahead and replace this silicon atom by, let's say, phosphorus. Okay, phosphorus now has how many valence electrons? 5. So therefore the phosphorus has 4 electrons that it forms a covalent bond with, right? And this electron can easily be released above 0 Kelvin, not at 0 Kelvin. If you increase the temperature, much easier it gets released, okay, and is available for conduction. Okay, this act of replacing the silicon atom in the lattice with another atom like phosphorus or boron, which is trivalent, is called doping. Okay, this process is called doping. Now once this free electron is released from phosphorus, what happens to the charge of that phosphorus atom? Yeah, so this will become positive, right? The phosphorus atom, the electron is now free, available for conduction. The phosphorus atom is a positive charge, but it is immobile because it is in the lattice, it's stuck in the lattice. It does not contribute to any current or current flow in general. Okay, so now the question is, at room temperature, how many such free electrons will I have? Okay, it turns out that if your doping is high enough, then at room temperature all the atoms are ionized, phosphorus atoms get ionized, and therefore the number of electrons at room temperature is just the doping concentration, right? And this is, the phosphorus atom is giving an electron, so it's called a donor, right? And the concentration of phosphorus is Nd, the doping concentration, right? This is doping concentration. Typically it is about 10 power 15 per centimeter cube. Okay, notice that it is 5 orders of magnitude higher than the intrinsic silicon free electron concentration. So that's why I am not worried about what happens to this free electrons that come from some of the silicon atoms. That also happens, but that number is so small I can neglect it, right? So effectively I have like number of free electrons at room temperature is 10 power 15 per centimeter cube, right? Now how many holes are there in this doped semiconductor? So it turns out that there is a law of mass action that determines that. Law of mass action. Okay, what does this say? It says that the concentration of electrons into holes is a constant, and that is basically Ni square. Okay, so therefore if N equal to Nd, what is P? Ni squared by Nd. Okay, now there is also another equation called the Maxwell-Boltzmann equation, okay, which just tells you that if I have 2 points in a semiconductor, okay, this is my, let's say, silicon here. Some reason I have caused a charge imbalance, it doesn't violate conservation of charge, but there is more concentration of electrons here, N1 and N2. Okay, and let's say N1 and N2 are different, then it turns out that there will be a potential difference between these 2 points, which is basically psi 1 2, and the relation is given by N1 by N2 is e power psi 1 2 by kT by Q. K is the Boltzmann constant, T is the temperature, Q is the charge of the electron. Okay, and this is important to know, kT by Q at room temperature is approximately 25 millivolt. Okay, you can work it out, just substitute T equal to 300 Kelvin, work out the constants and you will get this. Okay, so you should know this number, 25 millivolt is an important number for a digital designer, right? So this is basically called is it called Boltzmann equation? Yeah, it's called the Maxwell-Boltzmann equation, not just the Boltzmann equation. Okay. Now, what happens? So what I've done is, with this equation here, I have completely bypassed this theory of Fermi levels and other things. I have abstracted out all that I need for this course, right? And in fact, you can even go ahead and do a lot of device derivations using just this assumption. Okay, the book called Cividis actually does it like this. The MOS transistor, it works exactly like this. So this abstraction is very, very useful, not just for digital design engineers, it's also good for device guys. Now what do? I can't do much with just N-type semiconductor, right? So that is the donor semiconductor is called N-type semiconductor because I have more electrons than holes, right? I can take 2 semiconductor blocks which are doped differently and connect them together like this. Okay, so let's say this is Nd, this is Na. So instead of phosphorus, if I put boron is trivalent, there's going to be 1 electron absent and therefore it's like a hole that is available. Okay, that's the abstraction that we need. So I have an N-type semiconductor here, I have a P-type semiconductor here, right? So I can even maybe say that dopant equals phosphorus and here it is boron. So now what happens? You basically have excess electrons on the N side and excess of holes on the P side. So therefore they will now start diffusing, right? So the free electron from this side will go here, the free hole from this side will come here. Remember that once the electron comes this side, what happens to the atom from which that electron was released? It's a positive charge. So what happens is, effectively on the N side you will have immobile positive charges like this, and on the P side you will have immobile negative charges that are formed. Okay, so ultimately there will be a region like this here and a region here. This is called space charge region. Space charge region, basically it says that there is no free electron or hole that is available for conduction there, because moment you have a positive charge on the N side and a negative charge, you will have an electric field coming from the N to P, right? You have an electric field here. So if any free electron enters that region, it will be driven the other way. If a hole enters, it will be driven in the direction of the field to the other side. So this is basically devoid of any charges, and you will have what is known as a built-in potential across this region, space charge region. Okay. So now let's calculate how far this has to go, okay, on both sides. Let's say that this went up to a distance of Wn and this went up to a distance of Wp. Okay, on the P side, the distance of the depletion region is also called a depletion region, by the way. This is also called depletion region. Okay. How do I relate Wn and Wp? Huh? Yeah, basically charge neutrality, right? So therefore, if the concentration of electrons, right, on this side is Nd, I mean concentration of dopant atoms is Nd, right, then the number of positive charges is what? Q times Nd into Wn into the area. Let's say the cross section is like this and this is the area A, right? Then into A is the total volume, Wn into A is the total volume. This is the total charge. This has to be Q times Wp into Na into area. So Wn into Nd is Wp into Na. So what does this basically say? It says that W into N is a constant. So the main takeaway for us here is, if Nd is much greater than Na, let's say, it implies that Wp will be much greater than Wn. Correct? Clear? So now, okay, we have a relation between Wp and Wn, but what about Wp plus Wn? How far will that go? So that will go only as far as I am now what do I have? I have in a semiconductor I have 2 points. Point 1 is here, this is point 2. There is an electron concentration at point 1, there is an electron concentration which is different at point 2, right? And therefore they have to be related by the Maxwell-Boltzmann relation, right? So they, which basically says N1 by N2 is e power q times built-in potential VBI by KT, right? This, let me call it VBI. Now what is the electron concentration at point 1? N? Yeah. So N1 equal to Nd. What is the whole concentration at point 2? Yeah. So the P2 is Na, which means N2 is how much? Yeah? Ni squared by Na. Therefore, I can now divide this as Nd by Ni squared into Na equals e power qVBI by KT. Therefore, built-in potential is KT by Q ln of Na Nd by Ni squared. Okay? This is all we need from the semiconductor device physics for us to go ahead and understand all of MOS transistors for digital design. At least first order short channel effects, all that we can handle with this. Okay?